So there's this NASA program, which the name of which I really, really like. It's called Living with a Star. But I would argue that it should be called Living in a Star or Living within a Star at the very least. The sun is a star, and it's a fairly ordinary kind of star. It sits in the middle of the solar system, and it converts hydrogen into helium and produces light as a byproduct. But from the astronomical perspective, it's a rather unexciting object. In many ways, it's just one in billions. But it does produce the light and the heat that sustain life on Earth. And although it's not about to undergo any dramatic change anytime soon, within the next 5 billion years, the sun does vary. It varies in many ways, and it varies in ways that affect us. And probably the most noticeable one of these for us is the solar cycle. Solar cycle is just the variation of the number of sunspots that appear on the sun's surface as a function of time. And sunspots, we know today, and for those of you who don't know, are just very strong concentrations of magnetic field that pierce out through the sun's surface. It's actually just the footprints of that piercing out of the magnetic fields. They appear dark against the surface because they're cooler than their surroundings. They're cooler than their surroundings because the fields inside them inhibit the propagation of energy outwards. So the number of sunspots waxes and wanes within an 11-year periodicity, but there's a host of other things that changes with this 11-year cycle, such as the sun's irradiance, the flux of particles that come from the sun, the magnetic field, the number of eruptive events, and so on and so forth. The important thing is that all of these things are ultimately attributed to magnetic fields. Now, the term space weather refers to short-term solar-driven events and their interaction with the interplanetary medium in the neighborhood of the sun. And solar storms actually are coronal mass ejections and solar flares, you might have heard the terms, impulsive events in which the sun releases large amounts of energy and or particles into the interplanetary medium. And because they originate from sunspots, they tend to happen at a higher frequency of occurrence closer to the maximum of the solar cycle. This is a beautiful image of a filament eruption. A filament is just a large amount of solar material contained and sustained by magnetic fields. And when the energy buildup and the twist buildup in these fields is large enough, these things like rupture, erupt, and send out all of the material into space. And when this happens aimed towards us, the effects on Earth can be seen a few days later. In this case, it was in the form of a beautiful aurora. But the effects of space weather on Earth can actually be quite damaging, because space weather has the capability to disrupt systems which our technological society has come to depend on very much, like GPS, cell phones, power grids, et cetera, So the magnetic field of the sun is kind of swept out into space in the form of this spiral pattern. It's called the Parker spiral. And any event that takes place on the sun kind of travels outwards, somewhat following this spiral. And with this field, this is called the interplanetary magnetic field. Where this field meets the Earth's magnetic field, we call that boundary the magnetopause. And the Earth's field at that boundary is pointing northwards. So for a space weather event to have an impact, a severe impact on us, several things need to happen. One is that obviously it has to be directed towards us. So if it comes out of the backside of the sun, no way. The second thing is that the magnetic field of this event, of the interplanetary medium, when it reaches the magnetosphere, needs to be pointing southwards so that these two fields kind of cancel partially each other out, and it kind of peels off the magnetic shielding that protects the Earth. So to better understand and forecast space weather, we need to understand all of the links in the chain. One of them is like, how does the sun generate its magnetic fields, the solar dynamo? How do these fields come up to the surface in the form of sunspot? What is the 3D topology of these fields? What makes them erupt? This sequence of images shows a coronal mass ejection as it leaves the sun, and it travels out into space, and it kind of changes its structure as it travels out. It kind of unravels its topology. So we need to get a grasp also on how these changes in topology happen as the things propagate through space, because what we ultimately want to know is what the direction of the magnetic field when things reach the Earth is. That's what matters. So I hope, well, this number here is the solar irradiance at Earth, which is what most climate modelers really want to know. But I hope I've managed to convey the importance of the magnetism of the sun as well as just the irradiance value. Because in order to preserve life as we know it on Earth, we really need to understand the environment in which it exists. And whether we want it or not, we actually live inside the magnetic field of a star. and we're kind of subjected to this temperamental behavior. Thanks.